Let's explore now more consequences of the least upper bound property. In particular, let's look at this theorem on the existence of nth roots of possible reals, of positive reals. Okay, so what we want to do here is given a positive real number x and an integer number n. So we want to find the nth root. Okay, we will write the nth root of x, or also x to the 1 over n. So we want to know if this exists or not. We already encountered this type of thing with the square root of 2. There, both x and n were 2, or the square root of 3. X equals 3, n equals 2. Okay, so here there are several things we need to show. First, it says there is a positive real that is the square root, but also there is a second statement here that says that there is one and there is only one. Okay, so there is a uniqueness statement. So those are two things we need to prove. Okay, so let's get to it. So proof. First thing, let's get that out of the way. So the nth root, is unique. Okay, so this I leave for you to do. Just keep in mind, whenever you want to show that something is unique, just assume it's not. Okay. That means that there are two of them, and see that that cannot be. Okay. All right, so that out of the way. So then what is left is to show that actually there is one. Okay, so two. Here we need to, let me reflect for a moment on the strategy. Here we are planning to use the least upper bound property. So actually, before we get into more details, let me discuss the general strategy so that it feels less random. Actually, a strategy to use the least upper bound property Okay. So let me make more space here. In R. So this is the general strategy in a proof, okay? So the first thing, step one, so the least upper bound property in R means that for every subset of R, there is a least upper bound. So first, if we want to apply that, we need to define an appropriate set E, some set E that is convenient, typically a set E of the numbers that satisfy whatever property we want. Okay. The second step, we need to show that, I mean, we can define any set we want. We need something that is useful. So we need to show that E is not empty, okay? Because if it's empty, we are done. It's not going to work. and has an upper bound. Okay, so we want to use the least upper bound property. So for that, we need to know that the set E is bounded. Okay, so once we know it's bounded, then we can use the supremum of E. Okay, then the supremum of E exists in R. Okay, remember this is a property that we didn't have in the rational numbers, for example. So here it's important, the least upper bound property. Okay, this is because of the least upper bound property. Okay, and then the last step, this is an outline of the strategy. The last step is to connect this, let's say, with the rest of the information we have. Okay, so this is the outline. We have seen other proofs already. They follow basically this outline. Okay, so then let's get to it. So step one of the proof was to show the uniqueness. So let's show now that there is actually an nth root. Okay, so we want to show there is y such that y to the n equals x. Okay, so for this, what is the idea? Let's say we have here the set E of the numbers such that when we raise them to the power n, we fall short of x. They are less than x. Okay, so let's define that properly. That will be a step one of the strategy. E is the set of positive numbers, positive because we want them to be a root, such that t to the n is less than x. Okay, so the idea here, we have our set E, okay? And our guess is because all these numbers, when you raise them to the power n, they are less than x, okay? Maybe if we go all the way to the extreme, maybe there's an equality. And in that extreme, that would be, you see, because we have here the upper bounds. So the least upper bound, that would be the supremum of E, okay? That is our candidate to have an equality. So the question is it true? How should we call this supremum? Let's call it Y. So is it true that y to the power n equals x? Okay. So this is the big question. Now, notice here, the supremum. I mean, the supremum is the perfect candidate, right? Because it's right in the transition from being in E that the Tn is less than x to being outside that the Tn is bigger than x. Okay, so then there should be a moment there in the transition that Tn is equal to x, but that is not obvious. It requires a proof. So let's get to it. So in our strategy, we saw this is 2.1. So 2.2 would be to show that it's not empty and bounded above. so that all this thing I said about the supremum of E makes sense, because otherwise it will not. Okay. So to see that it's non-empty, it's enough if we find some element that belongs to E. Okay. So after some guesswork, you may try this number x divided by 1 plus x. This one belongs to E. Okay. So this I leave for you to check. Okay, what you need to check is that x divided by 1 plus x, all of it raised to the power n, is less than x. Okay, but it should, because if you, now the hint here, if you don't want spoilers, just pause the video. The hint here is that when we divide x by 1 plus x, and we have something, because x is positive, we have something smaller than 1, okay? So what happens to a number that is smaller than 1 when we raise it to a power n? And you continue from there. And now there's one second thing that we need to, this means, the first means that E is not empty, okay, because there is an element in E. And then we need to show that that there is an element, that there is an upper bound. Okay, so for this is enough to show that the same t is bigger than 1 plus x. Okay, and therefore, sorry, that if t is bigger than 1 plus x, then let me write it properly so that we don't get confused. There we go. If t is bigger than 1 plus x, then t is not in E. Okay, and this also you check. Okay, therefore, this means that 1 plus x is an upper bound, okay, for E, let's say. Okay, here again you need to use, because x is positive, 1 plus x is bigger than 1. And what happens when we raise a number bigger than 1 to power n, okay? That's the line of thought you need to follow. So now 2.3, once we have this, we can define y equals the supremum of E. Okay, now this is good. And we know that this exists in R by the least upper bound property. Okay, the least upper bound property, well, let me write the whole thing. In R, okay. And now the last step. So if we go back to our game plan, so we want to show that that in fact, here it is, y to the power n, the supremum of E to the power n equals x. Okay, and how do we do that? Well, a strategy here would be to, if you want to show that y to the n is equal to x, that's very, that's an identity, that's very good. It's enough if you show that it cannot be anything else. So let's rule out that y to the n is less than x, or that it is bigger than x, and then we are good. Okay, this is a by contradiction. Okay, so that's going to be the rest of the proof. So I'm going to do the proof slightly different from the book, okay, because when you write math, you don't write math the way you think math, okay? So you think math, you think about the main idea until you get a proof. And once you have a proof, when you write it down, you try to make it short and elegant, but that comes at the expense of the reader will feel like, where did this come from? I would have never have thought about this, you know? So you can read the proof from the book, which is short and elegant, but here what we are going to do is just like getting the idea. Okay, it's the same proof, just the 2 points of view, how the book presents it and how you think about it. I think that will be more useful for this course. So without further ado, assume yn to the yn to the y to the n less than x. Okay, let's box this. And here, so we have our y to the n, we have our x, and somehow the idea for the contradiction, we want to see that this cannot be. Okay, and remember that y is a least upper bound. So we need to find some type of contradiction with being the least upper bound or with being an upper bound. So what we are going to try to do here is to find some, let me call it an in-between. That's not a technical word, but it's clear, right? We want to find an in-between here between yn and x, okay? So let's write it in a simple way. I want something that is between yn and x, and I want it, for simplicity, of the form y plus 8 to the power n. Okay, just to keep things simple. Why is this helpful? Because then, let's say 8, I want 8 to be positive, okay? So that it's on the right of yn. So why do I want this? Because then y plus 8 is going to be an element of, if y plus 8 is an element of E, okay, then we have a contradiction with the fact that y is an upper bound, okay? You see, because automatically we will have an element y plus 8 that is bigger than y, but that is bigger than the upper bound, okay? So that would be the problem. So here's the contradiction, okay. All right, so we have two inequalities here to show, okay? The left and the right one. So the left one is clear as long as 8 is bigger than 0. Okay, so that's a condition that we need to remember for later. Okay, that's for now. From now on, we are assuming that 8 is positive. And let's see if we can prove the other inequality. So we want to prove that y plus 8 to the power n is less than x. And this for some 8 bigger than 0. Okay, so that's what we need to find, some 8 that works here. Now we are going to use a property so you see, because there is a sum y plus 8 and then a power n, we would like to use the expansion of a power of a sum somehow, okay? Some property related to that. So if you think about it or look different books, you will find this property that says that if you have two positive numbers, let's say a is smaller than b, then b to the power n is less than a to the power n plus b minus a. It's not going to fit here, so let me move things around. B minus a times n times b to the power n minus 1. Okay, and there are different ways to prove this. It follows from convexity, or it's also a first order Taylor expansion, but we shouldn't use that because we will prove that towards the end of the semester. So we shouldn't use things we haven't proved. But lucky for us, there is a very easy proof using that, well, using that n is an integer. So if I look at the polynomial bn minus an, I can factor this at b minus a times b to the n minus 1 plus b to the n minus 2 times a plus and so on until a to the n minus 1. Okay, and here comes the fun thing. So a is less than b. A to the n minus 1 is less than b to the n minus 1. So we have that this is less than b minus a. Remember, this is positive. Times how many terms do we have here? No. We have n terms. Okay, so here we have n times. You see what happened, no? B to the n minus 1. The second is b to the n minus 2 times b, and so on. We will always have a power n minus 1. So this is less than n times b to the n minus 1. And that's what we wanted to prove. You see, because now we can move this a to the n to the other side, and we are good to go. Okay, so we are, this is like a parenthesis. Okay, typically you will write this as a lemma before the theorem, or you will just make a comment very quickly, okay? That's what the book does. So we want to apply it to this particular case. So in this particular case, what is A and what is B? So A is the smallest, so we are going to use Y for A, and B is going to be the largest, so it's going to be Y plus 8. And because 8 is positive, we have that B is bigger than A. Okay, so then we can apply this property. So Y plus 8 to the power n less than Y to the power n plus the difference between B and A is 8 times n times, times B, Y plus 8 to the power n minus 1. And now I would like to solve for 8, but it's kind of problematic because it appears here and here. But since we don't have an equality, we just want an estimate. We can say, well, okay, let me assume that 8 is less than 1, okay, that it's bounded, so that I can just get rid of one of them. Okay, and then you see now it becomes super easy to solve for 8 because there's only one. Now you're thinking, but why would you do that? Why would you take 8 less than 1? Well, because it's convenient. If it works, we have a theorem. If not, we need to try again. Okay, so let's see what would 8 need to be. So remember again, what did we want in the first place? We wanted to show that Y plus 8 was less than, to the power n was less than x. So that's my question for you. Is this less than x? And yeah, let's see if we can force that. So 8n y plus 1 to the n minus 1 less than x minus y to the n. Okay, that means 8 less than x minus y to the n divided by n y plus 1 to the n minus 1. And actually, this is what, if you read from the book says right away, let h be between 0 and 1 and less than this quantity. And then you may feel like, where did that come from? This is where it came from. Okay, notice that this is positive. Okay, otherwise we would not be able to do this, okay? Because remember, we are assuming this, that h is positive and that h is less than 1. Lucky for us, these three are compatible, okay? Because if x minus y to the n divided by n, blah, 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 if that is less than 1, good for us. If it happens to be bigger than 1, then any h that is less than 1 works, okay? So you can take like as small as you want. As long as it's positive, it's going to work. And then we are done, because by definition, the way we picked h, so the way we have picked h, we have y plus h to the power n less than x. And this is by definition. That's what we wanted to prove. So we are good to go. Okay, remember, we wanted to prove that there was this in between that I called the y plus h to the power n, that was between y to the n and x, because then we were able to find a contradiction. So we have shown that that number exists. Okay, so we are done with this first part. Okay, so we need to do the second part. So let's assume now that y to the n is bigger than x, and this will finish the proof. So let's do it. So in this case, it kind of flips things around. Okay, now the y to the n is bigger than x, and we want to find the in-between. And let's call it y minus k. Okay, now we want something in between x and y to the n. And now, because we are going to the left, we, instead of plus h, we call it minus k. Okay, so how does this work? So why does this help? Because then y minus k is an upper bound for e. That doesn't look good. Okay, so that's a contradiction. With the supremum of e, which is y, being the least. This has to come up somewhere, okay? The least upper bound. Okay, and here the problem is that y minus k is strictly smaller than y. So we have found another upper bound that is smaller than the least upper bound. That cannot be. Okay. So again, of the two inequalities that we want to prove, there is one that is obvious as long as k is positive. So that we need to keep in mind. We want to show that x is less than y minus k to the power n. Okay. All right, so we will use the same property as before because it's still a similar type of computation. So let me copy it here, b to the n less than a to the n plus b minus a times n, times n times b to the n minus 1. Okay, and here what are we going to choose? So we are going to choose b is the largest. So that's got to be y, and a is y minus k. So then the two of them together y to the n less than y minus k to the n plus b minus a, which is minus k. Okay. Sorry, b minus a is plus k times n times y to the n minus 1. All right. And here, you see, here we have already part of what we need. So let's write it in a format we can use. So let's move everything to the left, everything that we don't need. Okay. And now we want this to be, so we have already the bigger than, we have it here. So let's be bold and let's say maybe this can be equal to x. Why not? We only need to, the only degree of freedom we have is k. So let's see if we can solve for k. So k would be y to the n minus x divided by n to the y to n minus 1. This is positive. Okay, why is this positive? Because the numerator is positive by the assumption. Okay. This is by the contradiction assumption. Remember, we are in the case yn bigger than x. This does it. This is positive, perfectly good. Okay, so then again, we have been able to find the in-between that we wanted. So everything was dependent on us being able to find this y minus k to the n. We have shown that we can find k that satisfies this. So now we are done with this proof. The homework for you is to read the proof from the book and compare the two styles. Okay, the style here that is the direct proof, the way you would think about it, and then the way you write it down in a book or in an article. Okay, that is more condensed, but it hides where the ideas came from.